Hello and welcome everyone. Thank you for joining us for the second day in our workshop about case hole logging with Mr. Mustafa Hagak. Today we're going to be in our second day, and I would like to remind you about the courses that we're going to have in August 9, which is going to be about processing and interpretation for borehole wireline image. And we will be telling you the date for the next course, what is going to be about practical and theoretical geomechanics for subsurface applications. So if you're interested in any of these courses, please contact us through WhatsApp or sending a message through LinkedIn, and we will be glad to give you more information about it. So I'm gonna give now the word to Mr. Mustafa Hagak to start with our second day in case hole logging.
Thank you very much. Did you see my presentation now?
Yes, we can see it.
No? Okay. Good afternoon, everybody, and good morning, whatever you are, where you are. Today, I will continue with yesterday's session. Today, I will talk about continue in discussing the introduction to case hole logging. Yesterday, we discussed the PLT. The PLT and yesterday I discussed with you the cement bond log and the corrosion log. Today I will discuss another two topics. It's are very crucial for reservoir management and development. The saturation behind the casing and production logging, PLTs. Okay. So for the people who didn't attend yesterday with us, as I said, unfortunately this one. Okay. The oil field life cycle started from exploration, appraisal, and development, production, and then abandonment. So there is an award that says that if you cannot measure it, you cannot manage it. This is Mr. 𝗟�𝗱𝗏. So what you will what you will measure it? How do you measure it? Measuring meaning a character evaluation and the characterized. Okay, this is the basis of appraisal and development and the production. So this is the workflow for reservoir characterization, starting with reservoir description, meaning that you have geometry, properties, contacts, and to understand the performance and to make a proper monitoring. All the results of these milestones are going for 3D to optimum development. And development means that you will drill new wells or enhance or conduct enhanced oil recovery. The results of monitoring the reservoir and the development are updated in the reservoir description again, and we will go for the same loop. The petrophysicist has a contribution in this cycle or in this process. The petrophysicist can deliver in operations, can deliver in reservoir surveillance and studies. In operation, he can he interprets the open hole logs and acquires the data of open hole logs. And also interpret the cement and corrosion logs while the rig on site, and also in surveillance while the production. He monitors the water saturation change behind the casing, the topic which we will discuss it today, and the zonal contribution and the production problem. This is also we will discuss these two topics today. And also he can gives hand in AOR. Then in the reservoir studies, he can have a great input in geological modeling, AOR, seismic inversion, geomechanics, unconventional, and so on. Okay, a log is just a plot between x and y. X is the depth, y is the depth or the time, or time versus x, which is a which is a physical properties, any property, porosity, density, resistivity, just on x-axis. Okay, the wireline tools can convey or can go to the well using three methods or three techniques mainly. Either wire line if the well is vertical and less than 55 degrees inclination, and coil tubing if it's horizontal, and if it's horizontal or highly deviated more than 55, and or tractor in case the hole highly deviated welds more than 55 degree. Well logging objectives, as I mentioned yesterday, we have open hole logs for formation evaluation and seismic calibration, lithology, chillness, bed thickness, porosity, permeability, water saturation, formation pressure, fluid sampling, formation image. And cased hole logs is monitor water saturation change behind the casing, and zonar contribution and the production problem, borehole casing and integrity, borehole casing integrity and the condition. The third objective, we discussed it yesterday. Today, I will talk about PLT and monitor water saturation change behind the casing. Also, for the log data acquisition strategy, as I said yesterday, we have a production versus time. And as you see, for the exploration phase, and the number of wells is increasing, significantly increase, and then the number of wells start to be flattening a little bit with the development, and the rate also change, and the production have declines or increased based on the secondary and tertiary recoveries. And most of the exploration phase, we acquire open hole logs. Most of the wells, while this one in beside, but we increase the number of cased hole logs more in while the development the well. Till we have a decline and abandonment, we run corrosion log for safety. And also take in consideration that it's if you drill a well and you will not acquire the data on it from it, it is difficult to acquire the data later on. خلاص, you lost this area. Okay. And well stages is drilling, logging, casing, and the production. Today we will talk about the last phase. While the production, we have they have produce oil, and the water is replacing this oil. And if this oil is in healthy process or not, this water is in a healthy process or not. And also we have to understand which zones are contributed and so on. PLT. So today, this is just the start of the today talk. Production logging application. Evaluation. First of all, how to evaluate production profile distribution, zonal productivity, matrix versus fracture and fault production. So you have oil, and you want to know from where this oil comes, or if you have water or gas. So you have a zonal productivity and the production profile distribution, matrix versus fracture fault production. This production comes from matrix or from fracture or from fault. Monitoring a production profile change by time. If you run two BLTs with different rate in different times, you may have a change in rate, and I will show you an example of that. Fluid type change, water or gas breakthrough. So now if you drill a well, if you run BLTs in 1980, something like this, and you have oil, and in 1985 it start to produce water, you want to know from where this water comes. So the fluid change, the type of fluid should be investigated by using BLT. Diagnose a source of high GOR or water cut. Okay. Detect the leak of and cross flow. As you see here, there are some cartoons. Here you have an oil sand, and this oil sand, this packer may be leak. Okay, and go to the water sand. This is some sort of leakage. butter leak, or you may have channeling from water sand in the top to oil one to the source. So these type of channels and the cracks and should be investigated. Okay, butter leak, channel of the channel in the cement itself. Okay, and also plus joint leak here, as you see, this joint it may be leak here like this one. Okay, and also sieve zone when you have high pressure zone versus low pressure, so the oil may go from this one to this one. It's called safe zone. And also we can use in the PLT in production enhancement and data for planning work over. If you wanted to work over a well, you should investigate and go through all the PLTs and the TDTs and RST, any logs run in this well, you should investigate it. Completion and the treatment effectiveness. Okay, sometimes you run completion and this completion is not good. Okay, for reason or another, so you may be recomplete the well for with another strategy. The PLT sensors. Okay, PLT, what you are mainly or يعني in summary, what you are looking for from the PLT, you are looking for rate and hold up. Hold up means how much oil, how much water. This is uh, uh, hold up. Hold up is how the fluid you have, it's partition, it's the partitioning into gas, oil, water. How much of oil, how much of gas, how much of water. So rate for vertical wells, we have a spinner and water flow log. For horizontal wells, we have a spinner's array and water flow log. Okay. Hold up in vertical, you have density or gradual manometer, temperature, pressure. Horizontal, we have advanced tool, ghost, depth, and BVL. The vertical BLT measurement, it's the tool is about 30 to 35 feet. Okay, it's a main measure the flow rate, fluid velocity measurement using a spinner. We have one spinner. It's called the conventional spinner, conventional flow meter here, and the fluid density measurement, differential pressure graduomanometer, and the nuclear fluid density. Okay, wall bore temperature. So the PLT consists of spinner, graduomanometer for density, temperature, and the pressure, and XY caliber. So this is the four tools within this PLT tool in vertical. Okay. Okay. I will talk about tool by tool in briefly. So in brief, so the graduomanometer, what is this? It reads at the density of the fluid. What does that mean? That means that it's I have in the borehole itself, we have oil and water in the bottom. Where is the oil and the bottom and while the production? Where is the oil and where is the water in the borehole? So this is the function of the use of the graduomanometer. The tool uses pressure differential, differential pressure between 2 points. Okay, 2 feet apart. So they have an silicon oil, it's chamber, and the tool uses pressure differential between two pressure sensors spaced known distance 2 feet to infer the density in the fluid between these two. So rho, so the density is pressure 2 minus pressure 1 divided by G H, which is 2 feet, and G is constant, plus rho silicon, and we have this one. So now we can know what is the density of the fluid. Unfortunately, this tool is not working if not working well in case if you have deviation or the well deviation. So as you see from this graph, the tool deviation and the density, and this is the envelope, the dynamic range of the tool. So if the tool is about 60%, so the density, it will be affected or reduced or need to be corrected to 60 to up to 40%. right? 40% is not right from the tool. In 80 or in horizontal, it's about يعني almost 100% is not right. Okay. Now it is يعني this the concept of the density or the gradual manometer here. If we have make a plot between density and water hold up, so from 0 to 100, okay, and water 100 water, it is the density of it, it's 1. And if it's zero water, it's 100% oil. So the oil density will be on this line. So we have line between 0 oil to 100%, from 0 water to 100% water. So if we have a graduate, say, 0.8, so we can know exactly how much hold up we have. So if we have, say, this one is 0.8, this one is 100, so it's 0.9. So we may have about 40% water, and 40% oil, and 60% water. So this is look the fluid density in the PLT. This is example of PLT. We have an example. So here the density is about 1. It's mainly sorry, 1.1 is here. It's about 0.8, 0.9, and then suddenly it's go to 1. So this is the bottom, or the oil water contact, or the oil water hold up in the borehole itself, not in the formation. Doesn't we will not work on formation. We will work on the borehole. So this is the the bottom of stagnant water in the borehole. Then temperature log. So now we finished the gradual manometer, the density, and now we will go for the temperature log. Temperature log is mainly based on the Wheatstone bridge. We have temperature sensor, so we have temperature sensor here, and this temperature, this resistance, the temperature, this resistivity or resistance, it's depend on the temperature. So all are constants except this one. So he can calculate what is, if there is any change in the Wheatstone, so he can know, he can define what is the temperature here. Okay, so the variation in resistance of platinum resistor is measured in using a Wheatstone bridge, accuracy plus or minus 1 degree centigrade, resolution 0.006 centigrade, and application downhole reservoir pressure, flow detection behind the casing, gas entry detection, fluid properties, conversion to surface conditions. Okay, so as you see here, the fluid temperature here, when you have oil entry here, it increases the temperature a little bit, and the water here is, because there is not dynamic, so it is less temperature, sorry, a higher temperature, and the oil here is less than water. As you see here, there is so you can know exactly where is the oil and where is the water. Okay, the temperature have there is an example. This is a geothermal gradient, which is from surface to TD, with about, so this is the geothermal gradient in the borehole. And here if we run temperature log, as you see, the entry of oil will increase it. Okay, and based on it is, there is any reduction or any profile, and then but for gas you will have a cooling on it. So this is exactly the temperature log. If you have a fluid comes from the hole, it's increase the temperature. If there is gas, it's decrease the temperature. Okay, so as you see here, this is the first entry, and then secondary entry, it's increase more, and then suddenly the temperature, the gas entry decreases this temperature profile. Pressure sensors. The pressure also is in the borehole. Okay, it's measure the fluid, the pressure in the borehole. Okay, so it's give me the downhole pressure. Okay, transient analysis, PVT conversions, flow detection. Okay, the types, there are two types of pressure in the BLT. strain gauge and quartz gauge. Strain gauge is a sensor. This resistor sensor, it's the same as Winston, and but it depends on the pressure. Okay. This pressure, its resistance change as pressure and temperature are applied. Temperature measured by separate sensor. Quick stabilization time, measure gauge pressure. Measure gauge. As you know, the pressure it's measured in either gauge or absolute pressure. Absolute pressure, it means the gauge pressure plus atmospheric, 14.7 psi. Quartz, it's vibrating crystal. Resonant frequency change with pressure and temperature. Temperature measurement can be measured using a crystal, better accuracy measure, measure absolute pressure, quicker in stabilization. Spinner. Now we have three sensors in the PLT, and this is the fourth sensor, which is the spinner. So the PLT has two spinners. One is called continuous flow meter, and one is called full bore flow meter spinner. Okay, the one the continuous, this one, the continuous one, it is flow for low and medium flow rate, fits in the gauge to be protected while running hole. While running hole, this spinner is moving, and this spinner is moving, and this spinner also is moving because it's the same as you have an this tiny fan or something. Like if you move it in the air, it will rotate the same exactly. So now we have this one is closed while running hole to not be damaged, and this one protected in gauge so it can rotate while running hole. Okay, not collapsed. Measurement in tubing and casing, not sensitive to small flow variation, low resolution, and different sizes. A full bore spinner collapses to pass through the tubing. This is the full bore spinner. Okay. Okay. This spinner, I want what about the main objective of it? How much rate we have? Okay, how much rate we have. So to define the rate, we have many parameters affecting this spinner. So we have to calibrate it for it. The spinner speed is affected by. So if the well is shut in and no flow, and you run in hole, the spinner will move. Okay, because of the speed of cable. And also, if you have different viscosities, the spinner will move with different speeds. So the cable speed, the fluid viscosity and density also affect the velocity of the spinner. Borehole diameter, the bigger hole, and the lower in speed. The smaller hole, the higher in speed. So, and fluid flow, and also if the flow, if the tool is stopped in any area, and the well is starting to flow, this flow will make the spinner to rotate. So from this, the factors affecting the spinner are density, viscosity, borehole diameter, cable speed, and fluid. What we need to know is the fluid flow. So we have to compensate for this, or we have to correct for this. This is therefore to define the fluid flow, the spinner should be calibrated to eliminate the viscosity, diameter, and the cable speed effect by getting the spinner data while the well is shut in. So now we eliminate this one and we run the tool. The well is shut in, no flow. Okay. Okay. And as you see here, if we have, this is the ideal slope, this is the tool velocity versus spinner, RBS, rotating of a spinner. So يعني logically if it's zero velocity it's a zero spinner. But okay, if it's zero velocity, zero spinner. But in shuttle, no, the viscosity will move this ideal one to either to the down or to the up, according to if you go up or go down. So increasing viscosity, increasing this, the increasing in this direction. Okay. So this one, it is the viscosity effect. Here is the diameter. As you see here, if the caliper increased, so the spinner increasing. Okay, as you see here, the caliper is less, and if it's higher, the spinner is less. And here the cable speed, as you see, if we can make an 100 feet per minute for the different and 80 feet per minute and 30 feet per minute, the cable will have the depth versus spinner. Okay, and as you see here, the cable speed it changed by the speed itself of the cable speed. Okay, so this is an just a brief on what is the how we design the PLT program. The PLT logging program, it's simply we conduct or we perform three passes at different cable speed across the interval of the interest. So we make an three. So we closing or shutting the well for little bit longer time, maybe 2 days, 3 days, just to ensure that the well is in equilibrium of everything. The pressure is good, stable, fluid start to be in equilibrium in the borehole, and so on. So perform three passes at different cable speed across the interval of interest. Perform spinner calibration. Determine fluid level. Detect cross flow if any. This is in shuttle, because if there is cross flow, meaning that there is fluid moving in the hole or behind the casing, and the well is shut in. So there is this is called cross flow. And in fluid conditions, wait for stabilized flow. So we start to flow the well. Okay, start to flow the well, and then how do you know that? And then wait till the pressure and the spinner and interest are stabilized. Okay, and record over the interest interval the three passes up and three passes down. We go for with three different cable speed, three up and three down. Okay, perform spinner calibration, identify the flow and the cross flow, identify fluid entries, record at station, and then if you have perforation, we have to stop with the BLT and flow the well above every perforation and record the spinner. And this is at zero cable speed. Okay. Uh, this is some sort of calibration. Velocity of the spinner, there is an average velocity. Why? Because the maximum, if the fluid is going in this direction, so it means that it's the maximum speed or the maximum flow at this one, and there is less in flow. يعني there is less energy on or force on this part. So we make an average. This average is just they calculated and the model based on the casing type and casing size and diameter and the flow rate. So they have a constant versus v of the measured velocity. So q it will be, what is this? Atom, atom. Hello,
Yeah, please, Mr. Hatem Akur, if you could.
atom Ashur. You shared your screen, I think.
Okay, I think you have the option to delete this.
Okay. No يعني تقريبا almost يعني okay. Do you like to ask this question or to continue?
Yes, but first, please, can you you have the option there in the bottom of your screen. Uh, you have the option to delete that. Where it says whiteboards. Or if you want, you can stop sharing and share it again.
Okay, just a minute. خلاص okay.
Mhm.
Okay. You see it now? No?
Just, yes, we can say it now. Thank you so much.
Okay. Okay. Yeah. There is one gentleman says that it was the LWD and okay. Nothing to do between cased hole logs and wireline logs. That the sensors are almost have the same concept, but in open hole logs is completely different conditions, right? Okay. So what I said that the Q, the rate equal area multiplied by fluid velocity. So this fluid velocity is not the maximum, not the minimum. No, it's the average velocity. Okay. From this one, we can define what is the rate of this one from the uh, spinner velocity. So as you see here in this one, we have production, we have how much of water and how much of oil, the percentile, okay, and also the cumulative production here production per zone. Here we have this one. It has we have 5,000 feet, 5,000 barrels per day. The rate. So from 0 to 1,000 to 5,000. So this is about 405, 4,400, 500. So this one it's producing about 3,000, and this one producing half of it. Okay, and as you see, this is the PLT. This is the spinner speed. It looks like this one, spinner profile, like this one. Okay. So from this one, we can make an just line here. This is 100 and how much this part and versus this part. It was a simple way. Okay. This is just an example of how we can make a calibration. So this is the point. These points are the shut-in passes. Shut-in passes. We make a trend to eliminate the viscosity, the cable speed, and the diameter. So this one, he says that it's we have the zero. We have we have an okay construct flow curve determines the flow rate in 15 RPS. So now we have in I wanted to know above a certain perforation we have 15 RPS. So for this 15 RPS is speed is about 67. Okay, so now from the zero shuttle, this 15 will equivalent to cable speed 150, right? 150. This is total is total speed due to uh, okay, due to what you call it due to الفلو and due to الفلو due to cable speed, diameter and the viscosity, but it has 67 feet per minute for the tool itself. So we have to subtract this 67 from this one from the 140 and multiply by this one by the diameter of the casing, it will give you the amount of how much flow across this area. So this is just an idea about how do we calculate it. Okay, this is an example of PLT. As you see here, we have this bottom part, the small part, it's 100% water. Okay, and then suddenly we have the most of the production comes from this part. What does that mean? Can someone put it in the messenger? What do you expect? This one. What will give you this huge oil production? Anyone? No? Put it
Yes,
in
we
the
can
chat.
hear you. Yeah, yeah.
Yeah. What do you expect is this type of formation or this type of porosity, this type of permeability give you this the contributed to about 2,000 barrels. This one is fracture. Okay, okay. So this one is fracture, right? It's the behavior of the fracture, right? And then we have a small part in this perforation producing in the top perforation producing just a small amount, and then we don't have any production from this one, and from this one they are not producing anything. Okay. Now this I told you that it's we have with BLT is we can have a change in rate. So this one in uh, so we have a change of rate. This one was producing by total rate 18 18 18 1800 18 1855, and this one producing 4,000 barrels. So as you see here, we have uh, this part is producing all the oil in this one, maybe another fracture. But if we increase the rate, it start to be go gradual the other intervals producing. Okay. Okay. So as you see, if the rate changed, we may have increased the zones which contributed to the production. Okay. With the same, almost the same water cut. He's 8%, 9%, and this one is total rate 1855, and this one is 40 50. Okay, the choke size 24, the choke size is 40. Okay. In horizontal holes, now we have a vertical hole and we have horizontal hole. Type. If this ability can be used in horizontal hole, the answer is no. Why? Because the borehole trajectory influence hold up and the fluid velocities. Okay. Stratified flow regime affecting spinner performance. So as you see, this is a cartoon of what the horizontal hole looks like. There is some peaks, troughs in between. There is no horizontal hole straight forward, except in very rare cases. So if we produce oil and water, the water will be stagnant in the bottom. The oil will be in the middle and the gas in the top. Okay. Unfortunately, there are some fluid in this direction, and also there is some fluid in this direction. Okay. Okay. Stratified flow regime affecting spinner performance. Why? Because in vertical hole, the spinner is perpendicular to the flow direction. But here, The spinner is not perpendicular. The spinner will you have three phases in the same time. Rock debris from barefoot completion plugs and damage the spinner. If the because barefoot, there are a lot of companies complete the horizontal hole as a barefoot. Barefoot means that's no casing, just open hole. And so this one, so this will lead to you have some debris damage the spinner. Fluid density measurement are not applicable for horizontal hole. El gradiometer is not working. There are two tools. There are many tools, but it's I will talk about today an 𝗪Sci from Schlumberger and the maps from Baker. Just two different technologies. Okay. Advanced BLC, advanced BLT in horizontal hole. The deviated and horizontal hole and will complex flow regime that affect the interpretation from the conventional production logging, right? Okay, so the horizontal, as I mentioned, the horizontal and deviated hole, the flow is not normal one. It's not coming from bottom to top. No, we have some horizontal, some segregation in the oil, in the fluid. Okay, and go up and go down. We have some debris and so on. Where the spinner gradient and pressure and temperature measurement become less reliable because of the limitation and application horizontal. So it is therefore have the ghost, okay, and flow view sensors are used for hold up and array spinner. So we changed the gradiometer and uh, gradiometer and temperature and pressure, or any hold up sensors by ghost and flow view. Both of them I can solve for three-phase application, three-phase hold up, right? Okay. What is the gas hold up optical sensor? Gas hold up optical sensor هو just a probe and he make a bubble counts, okay, and optical he can an refractive index. So if it's gas or oil, he can differentiate between from gas from liquid, from gas from liquid. So he make a bubble count. Where is the gas? Uh, where is the liquid? Okay, this is the gas hold up optical sensor. And the digital entry fluid fluid image tool deft, the flow view bubbles count is the same, but it's resistive. لا لسه. Oh, okay. Okay. Digital fluid image, it's deft. It's the same with low frequency for low frequency probe. It's a probe with electrical properties. So he can make a count, bubble count, and he can differentiate between oil and water. So this one gas fluid and this one oil and water. Both of them can give you how much water, how much oil, how much gas. Okay. Then array spinner, I will show you how what that means. This is the array spinner. This is one. We have this tool. It's called 𝗪Sci flow scan imager. It's have ghost. We have deft, and we have uh, many spinner, four in this side and two in this side and one in the bottom. And we have electrical flow about five optical or ghost and five deft. Okay, so I hope it's worked. No, not working. Anyway, yes. Okay, did you see it?
Yes, we could see it.
It's okay.
Yeah, the one from the oil field review, the one from the left.
Okay.
Yes, we could see it.
Okay. Did you see clearly?
Yeah,
Hello?
it was clear.
Okay. Now we will go for I will go for multiple array production. This is used by Baker or many tools because it's by Sondex. And Sondex is a manufacturing logging tools, a logging company. Okay. So we have maps. Maps. It's called the multiple array production suite. Sorry, suite. Okay. So we have in this tool we have three main parts. One is called cat, rat, set. Set is many spinners, array of 6 mini spinners. Okay, and can give you the velocity of each individual fluid layer as the same as FSI. Okay, and resistance array, it is rat. It's an array of 12 micro resistance sensors that try and water hold up. Okay, the whole of the pore whole conducted, but oil and gas are non-conductive. So this one can give you conductive and the non-conductive, like the depth in other tool, which is can give you the which water and which is oil. And also here is the capacitance array cat, which is small miniature sensors. It can give you what is the oil or gas and oil, because each one have a capacitance, okay, and dielectric constant. So these the three tools, it's a it's another technology. Okay, this is as an example of a zonal contribution. As you see here, we reached up to this point, and the rest we cannot go, so we have some fluid here. So this comes from the bottom, and then we have this interval. It can give you some oil and give you oil. Okay, and then all this part doesn't give anything, and this part, so the only two parts give oil, this one and the rest we don't know. But we have oil, but we don't know from where, because we still have an unlocked parts, we cannot reach to it. By the way, these horizontal tools, it's running on coil tubing, and the coil tubing have a lot of many problems in weight and long intervals. The coil tubing cannot reach to it. Okay, here there is another tool. We have water in the bottom. It comes from this fault. Okay, so now we have almost homogeneous oil production, but constant water comes from. So if there is a decision, just close this one and plug and abandon this part to avoid the water entry in this well. Okay. This change in rate in horizontal hole. So this in 2007, this in 2002, and this one in 2007 with different rate. So now in 2002 we have this like in fractured one, but with change in rate in 2007, it is little bit changed. That is more intervals contribute to the production. Spectral noise tool. This is it's another. It's PLT, but for vertical up till now, and it is by up as I know. يعني. I don't know if they have any version for horizontal or not, but spectral noise logging, TGT. Okay, it is Russian technology. Depends on what? Depends on spectral noise logging. Just like when you make something like that, if the gas comes from the formation, it make a noise. And or oil, if you have oil or gas, it comes up from the formation, it's make a noise. So a spectral noise. Spectral noise looking entry point of production and injection, communication with underlying and above unit, fracture and in matrix injection, short string production detection through the logging string, high precision temperature. Why temperature? So we have a noise, okay, and we have a temperature log as well, okay. This temperature can give you any fluid movement inside the formation. Historical injection zone, static temperature profile, current production zone, flowing temperature profile, water breakthrough, water invasion zone, and multiple phase profile. Okay. This one, it's a fast response temperature, which can give you static and dynamic temperature, provide fast response and high resolution of the temperature reading that allow to interpret in terms of volumes and the production injection distribution. Okay. So a spectral noise tool, this has a very sensitive hydrophone. And what is this? It is when the fluid comes out to the formation, to the borehole, it make a noise. They modeled the noise to know if the fluid comes from near to borehole or from fracture or from reservoir matrix. This one doesn't matter with how far from the borehole. No, they modeled the frequency based on mathematical model, and they applied, and they know this type of frequency or noise. It comes from fracture or comes from reservoir from the matrix or from near borehole. So he can discover if there is a small channels and you don't and it's not seen by normal tool. So it is by using this tool. Okay. And also in addition to these tools, they have multi-sensor water hold up fluid salinity and density just to confirm. Okay. This is fluid velocity. This is how they model it. How they model the noise profile. So this is just a fluid velocity. So if it's the fluid velocity, if it's something like this, it will be 10 meter per minute. Okay, 5 meter per minute and 2 meter per minute. They are modulated. Okay, and the fluid type, if it's something like this, it's water, and here is CO2. Rock type, fracture limestone, double the porosity limestone, porous limestone, okay, and the tight sandstone. Okay, so they make an extensive work in mathematics and the modeling for this tool. Okay, as you see here, this is a fluid communication example. Okay, so this fluid, it's there is we have all this formation, and we have a channel behind the casing, and it is comes to here. This one showing that it's we have a channel behind the casing. Okay, okay, and here how to interpret it: borehole flow, fracture flow. Okay, and this is reservoir matrix flow, and there is a channel here. Okay, any questions before we go for this second one? Okay. Now I will go for saturation monitoring behind the casing. Any question?
You
Again,
have you have a couple of questions in the chat section.
which logs we can take without flow mode? Okay. If you have an if you have an PLT, okay, BLT, yeah, the BLT, it can it you should flow the well to know what is the contribution from where. If you have different, if you have in the surface you have some water, okay, water cut, and you have oil, so you wanted to know from where this one, so you have to flow the well. But if you say you expect that you have 5,000 barrels per day in a well, and it's produced only 2,000 or 3,000. So in that case, you have to flow to shut in the well completely, and to run the tool with no flow. If the shut-in, and maybe you have internal cross flow, the well is producing from the bottom, and a safe zone take this oil in the bottom one. And also the RST, no need to flow the well. Okay, the RST logs. يعني it's no need to, if you close the well, sometimes you don't have to the flow you have to, but anyway, by any means the flowing is good, because of if you shut in the well, some fluid will go again to the hole, or to the wall of the well, and in this case it will be some sort of invasion. Okay, so you have to flow the well to clean this one and produce. Did I answer your question? Do I answer to your question? Okay, if you're having ESP, semis or pump, يعني, then can we take production log? Oh, okay. Before we make any program for production logging, you should have very clear tubing from surface to TD with minimum 111 111 16, which is 1.68 for the normal tools, which is cased hole logging tools, and it's one, and with the no go valve, it's 1.9. If anything in between, no, you cannot run the logs. By the way, okay, the BLT in horizontal hole and in vertical hole, there is minimum of number of barrels to make the tool is working. I think is less than 500 or less than 1,000 barrels a day. The BLT is useless. Okay.
Hello, I have some questions, actually some queries. Suppose one wheel is having one SRP or ESP. In that case, but the flow pressure will not be sufficient, so that
Answer
it,
this.
yeah, okay. See, so it will be able to produce in those scenario. Suppose we have started getting some water or some zones, some thick zones or cross flow or something happens, then how will we find out actually which zone is exactly contributing how much? Because there will be pump actually. If we remove the pump, there will be no flow from the well. So in those scenarios, can we do some kind
You
of
have
production logging?
okay. Uh, you can make another, yeah, but it's at least you may run some logs. You know, don't. Actually, you have to sit with the petroleum engineering and with the Schlumberger or the logging company, right? They
Okay,
will find the solution for you. Okay.
okay, 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 okay. Okay, thank you.
But actually, but actually, if you have, I know that if you have a bump in the hole and this bump in obstructs the tool to go down, how can you? Okay, and this one, so if you remove the bump, how the well will produce without bump? Right.
Right.
So I think it should be discussed with the petroleum engineer. Okay.
Okay, 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 okay. Thank you.
Okay. Welcome. So water saturation monitoring behind the case. Objective. The objective is measure water saturation and its change behind the casing. Locate the bypass oil, understand water flood front, detect the source of water in case of water channeling. Okay. Tools, thermal decay time tool, TDT, RST, RPM. RPM, this is for Baker, and so on. There are three modes in this tool: Sigma mode, carbon oxygen mode, water flow log mode. And then I will talk about cased hole resistivity very briefly. Okay, the thermal decay time tool is Schlumberger called TDTP, TDT RST tool. Baker is BDK 100 and RPM. The tool is simply, it is just minitron, which is neutron source plus near detector and the far detector. It is 11116. There are two tools, 2.5 inch and 11116. But this one I don't use because most of the completion is it's fit with this one. Most of the completion in I think most of the wells or all the wells I say use this tool. Okay, so this tool is used for minimum restriction 2.625. This one minimum restriction. So if you run any production logging and you put the program, you have to look at the well diagram to know where is the minimum restriction all over the well. Okay. The the physics of the tool, it is not that difficult. We have the pulsed neutron is based on the fact that the neutrons emitted by source minitron, okay, minitron, to the formation around the tool till it's captured. So it is emitted a high neutron with high energy, okay, to till it's captured. The monitron have the neutron is with energy 14 mega, okay, electron volt, okay. Those are neutron energy starting with very high speed and inelastic collision. Inelastic collision, it means that it is hit the neutron and release gamma ray. Okay, so fast neutron more than one. It's fast neutron more than 1 mega electron volt, bounce of a nucleus, neutron from the tool, okay, characterized gamma ray fingerprint emitted by the neutron. This gamma ray, it's have each element in the formation have a peak in this gamma ray, okay, and this is some sort of spectrum like in it's used in ECS geochemical tools or something like this, okay. Then elastic scattering. After that, he lost a lot of energy till it goes to the thermal zone, thermal level. Okay. Okay. So it have a like billiard ball. It hits the neutron like a billiard ball, but it with nuclei without gamma ray, but it collision with the nuclei and without gamma ray emission. Maximum losses of energy with the hydrogen. So more hydrogen, more losing energy, okay. And then finally the thermal neutron capture, it's the thermal neutron, it reached from 14 megahertz to 0.25 electron volt. It's exponentially decrease or dramatic decrease in the energy, and this one, okay, captured by, and this one will go through the thermal energy and it will stay until it's captured by chlorine, boron, cadmium, and so on. And it emits gamma ray. Okay, so it's give another carbon oxygen. Okay, another spectrum. So there are two gamma ray, captured gamma ray and inelastic gamma ray. Okay, so this one is used for carbon oxygen. This gamma ray used for carbon oxygen, and the sigma part, okay, and this part is used for sigma part. Sigma is sigma. The word sigma or the term sigma is the readiness or the parameter sigma, readiness of the material to absorb a neutron. Okay, this scientific name in the is called the macroscopic cross section. So in TDT you call it sigma. Sigma is this part. Okay, thermal capture zone, this one. If you have more chlorine, you have more capture. If you have more cadmium, you have more capture. But it's now we are run this one to know what is the water saturation change. Water saturation change means that you increase the water in the formation. This water is saline, so you have chlorine in it. Okay, so this part is revealing or representing the salinity. This part revealing the increase of water in the area. Okay, this just more illustration. So in elastic capture neutron in first milli micro in 100 microseconds, the energy it's in elastic capture log CO2 carbon oxygen saturation, three-phase hold up, and lithology. Sigma up to 1500 milliseconds. Okay, sigma formation porosity, and borehole salinity. Water flow log, it's water velocity and water flow index. Three-phase phase velocity log, oil and water velocity using marker fluids. Okay, sigma mode. What is this? Illustrate. Okay. So standalone sigma. So we can measure sigma. Sigma it is just it's a parameter. It's measured. So we can make it a standalone. We can calculate saturation or compute saturation if you have only sigma. So a standalone sigma when formation water is saline, okay, more than 35,000 part per million. Before less than this, you cannot measure. You can use sigma for water saturation change. Okay. Estimate today change in water saturation using time lapse. So one more technique is you have reference sigma, and after sometimes you run another sigma, that the change between both or delta SW or time lapse SW, it is just can you know how much change in saturation. Okay. Monitor porosity through casing. T5 is the best characterized. T5 is, as I said, that it's the decline, and the hydrogen is reducing this one, so he can calculate each hydrogen index, so can retrieve porosity from this one. Okay. Production logging application, gas well, water well contact, gas well monitoring, borehole salinity monitoring. Okay. The tool is just a burst two bursts, one short and one long. The short one for borehole, and the long one for the uh, for the formation sigma. This is an example of the log. We have gamma ray, okay, and we have borehole salinity. Okay, as you see it, it's okay. And borehole salinity, okay, and we have RST sigma, and we have near and far captured, okay, an elastic ratio, and capture to an elastic ratio far. So near and far detector from the sensors, right? RST capture, and this is far, and this is near, and this is ratio of it. Okay, what's the importance of this sigma? As you know, most of the materials or the minerals have a sigma. Uh, Sigma, it's not high. Quartz is 4, calcite 7. But if you have halite NaCl, it's 700. If you have iron, it's about 200. Salt water from 30 to 130. Okay, but it's, if you compare it with these ones, it's high. If you have a completion, it will increase sigma. If you have more salt, more saline water, it's increase sigma, right? And where there is an boron which is used for to put it in the mud for to make the mud is heavy. It's called the boron. It's 20,000. This is a question how to calculate sigma. So sigma SW equal sigma log sigma matrix, just as just mass balance equation. Just okay. So sigma SW equal sigma log minus sigma matrix multiplied by porosity في sigma hydrocarbon and sigma matrix, and so on. So this one you can calculate by using this equation is sigma, and this is the different sigmas. Time lapse sigma delta SW equal sigma log sigma base. Usually, as a technique, we run after the drilling the well and set casing and the perforate and the production. We wait up about 6 months just to make the mud dissipated, and then we run sigma base. And after 1 or 2 years, or based on the simulation, we run another sigma to see if there is any water breakthrough, or the water front is going well if we inject, and or we have in a normal. But if you have a water cut increase, you have to run sigma to know where is this water. It is from where this water come first. Okay, this is a time lapse. Okay, this how to get the parameters in reality. So how much the sigma water, how much sigma oil, how much, and sigma matrix, it's easy. Okay, so sigma water is controlled by salinity, which is affected by temperature. So This is a chart from a 𝗟chị𝗹𝗴𝗶. You have salinity and you have temperature, so you can give you what is the sigma water. The same for sigma gas is controlled by temperature and the pressure. How much pressure, how much temperature, and you can go for this chart, so it can give you sigma gas with this value. And also for sigma oil is controlled by GOR and the API. So you have the GOR from the production and you have API from the PVTs, so you can note sigma oil. Okay. And also graphically you have this porosity for this is for matrix mainly. Okay. So you can know this is 0, 0, 0 porosity, and we have gas, oil, and water, and this is a sigma. You have it right. So you have a water zone, and you plotted porosity versus sigma from the log, and it will the extrapolation of it at 100 porosity. It can give you what is the sigma water, and what is the sigma oil, and you have oil saturation. This one, and if you have gas, this part. Okay. Water saturation monitoring. This is an example of how to monitor water saturation. Okay, so we have this one in 1996, 97, October, April 97, October 97, and this is November 98, and this is November 99. As you see here, this is the swept part or the increase. The light blue is the formation water or connate water. Okay, or right. So this one is swept. So the black blue, okay, the black color, it's showing how much water increased, okay, by time. So as you see, we have increase in water, okay, in water saturation behind the casing from year to another year. Okay, this is the sigma, and how it's this is the sigma for each one of this one. Okay, this is an example of how can we use. So either you stop, so either so the reservoir engineer and the petroleum engineer and geologist should take a decision what they should do. They will, because it's only for only 3 years. All this part is swept. Yeah, water saturation monitoring. This part are the same, right? Okay, as you see here, sweeping. Okay, so from the bottom, this one increased as well. The yellow color. Okay, this is the formation water, and but the water, or the oil water contact is start to be deeper, little bit deeper. Okay, as you see, deeper, 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 and deep. Right. Okay. What is the factor affecting sigma measurements? Sigma measurements is affected by salinity. Increased salinity means increased water saturation, therefore sigma will increase. Acid effect, because acid have HCl, and as we said, H and as a chlorine is increasing capturing, so carbonate formation usually is acidized to enhance productivity. So so acid increase sigma across the acidizing interval because of the chlorine ions. Consequently, it is increasing the calculated water saturation. So any increase in chloride, it means that calculated water saturation. Filtrate effect, when drilled, the mud filtrate invaded the formation based on the filter type, fresh water or saline water, sigma should be interpreted. Base log can be run after reasonable period of to allow dissipation of the filtrate around the borehole. Okay. Completion effect. Completion iron is very high sigma. So in sometimes, in the history, in the well history, you may find make a recompletion for the well and add more casing or something like this, or the tubing change, but it's unfortunately they don't mention it in the report. So it give you higher sigma and you calculate it as higher water saturation, but it's not. It is just completion or change any part in this one. By any mean, as a rule of thumb, if they work it over the well, all the RSTs finished. خلاص, it's not used anymore because now you have new condition. You have to wait until you have to dissipate the mud and fluid, drilling fluids, and run another sigma as a reference, new reference. Okay, so double completion, double casing should be considered in interpretation. Okay. This is an example of sigma. As you see here, this one is actually is calculated as, okay, as acid effect or depletion. So you have to know we have a lot of water saturation, but they did an acidizing. Okay, they did an acid job. So this one increased water saturation, but it's not actually. Because it is just by the effect of acid. Here, filtrate effect, as you see here, we have when we drill the well in open hole, we have high water saturation here, and this water saturation start to change to vanish, and because of it, this is filtration. Okay, it's filtrate. Okay, by time. Okay, the sweep also in this well we have the sweep is increasing. Okay, okay, by production, but filtrates dissipate. As you see here, the yellow color decrease in this direction or increase in this direction, but the filtrate decrease in this direction. Okay. Carbon oxygen mode. So carbon oxygen mode, as we say from the neutron burst, how what it is, it's from elastic inelastic capture. Okay, so SW change behind casing can be determined from sigma reading unless the formation water salinity is less than 35,000. Not enough contrast between oil and water. Sometimes this one, it means that we have fresh water. And yet, I don't know if there is this case is in some fields they have it. But if there is no contrast in sigma between both, we have to run carbon oxygen. Variable or unknown formation water salinity. Now you in equation of the sigma, you should know what is the sigma water. But if the formation water sigma is say 100, and you inject water with sigma with pressure, and they are mixed up, so you don't know what is exactly the sigma in the formation now. So you have to run a tool independent on formation salinity, which is the carbon oxygen. In case if water is injected into the reservoir, salinity can be higher, but still the resulting mixture is unknown to solve the equation. The time-lapse techniques cannot be used. You cannot, for any reason, the time-lapse is give you an ambiguous results. Water-oil contact, the tool can always differentiate between water and oil. Okay, the carbon-oxygen, the log we have far carbon-oxygen ratio, it's output from the logs. And here, before I start this one, as you see here, the energy, and you see the spectrum of inelastic capture. As you see here, we have a peak of oxygen and a peak of hydrogen. Okay. So he knows what is the far carbon oxygen versus near carbon oxygen ratio. So we have two signals. We have either water in formation and water in borehole, or water in borehole and oil in formation, or we have oil in borehole and water in formation, and we have oil in borehole and oil in formation. Okay, so this is the four possibilities of the relation between oil and water in formation and in borehole. Okay, so the tool responding to both borehole and the formation fluid. So it's responding to two parts, borehole and formation fluid. For a given lithology, porosity, pore size, casing size. So we have to know this before we start in carbon oxygen. A database of various configuration in the well available. Based on this input, a quadrilateral plot is constructed. Output is SW and hold up of oil. How much of oil we have? So we have oil, we have water, oil, and we make this envelope, and we plot the near carbon oxygen and the near and the far carbon oxygen in this one, and he can give you how much oil and how much water saturation and how much uh, oil. So we have 100% water saturation and zero oil. Okay, so you just plot the log here or here or here. From this envelope you can know what is SW and what is I. SW is comes from this one, and SW is XY, this one versus this one will give you SW. Water hold up, okay, هتساوي A or B, this one of this one. Okay, so we have quadrilateral plot. We have the data. If the data is here, so from this one we can know from this technique how much SW and how much water hold up in her. Okay, this is an example. This is just an example that we have time lapse here. Okay, we have time lapse here techniques. We have just a small depletion or small increase in water, but in 19, in another RST log, it give you all water. It's no possible. It's all water like this in just 2 or 3 years. Okay, what happened? They make a stimulation and acidize this one. So we run logs or RST sigma. It give you all water because all this one is affected by acid. Okay, but when you run carbon oxygen, it shows you how it that the top part is still, because the carbon oxygen differentiate only between oil or water, right? Doesn't affect with acid, so it don't give you an acid effect in this one. So but this one still have water, right? Water flow log. Water flow log inside or behind the casing channel, up or down flow detection, qualitative flow contribution of zone, source of water, water intake in horizontal hole, zonal contribution, replace spinner in bad hole condition in horizontal hole. Okay, so in horizontal hole, we make an water injectors, but we don't know where is the water goes. And if you run a spinner, no need to run all the PLTs because we don't have oil. We have to run a spinner. Spinner is not working, so we run oil water flow log in on stations to know where is the water go enter the formation. Okay, so what happen if you have a casing and cement and there is some channel or some cross flow from water comes from a zone to another zone behind the casing? The PLT cannot see it, but by using this technique you can know exactly where is the water, exactly where is it go. It's simple like that. Your high energy neutron activate your oxygen. So you have you have here you activate the oxygen, okay, and it will give you it will release gamma ray within 7.1 seconds. This time life. So he receive it after 7.1 seconds. So he can know that you have how much you will you have a time, you have the distance, and so now you can know what is the velocity and the ray and the diameter. It can give you the how much of water crossing behind the casing. So oxygen plus nitrogen هيديني all this one plus gamma ray. Okay, The 16-inch isotope is unstable and has half-life time of 7.1 seconds, so it decays to the first stage of oxygen by eliminating beta radioactive. It's followed by the emission of gamma ray. Finally, it's gamma ray, which is detected by the tool. Knowing the distance from neutron to specific detector and elapsed time between neutron burst and the peak of gamma ray count rate, the velocity of the water can be calculated. The velocity of the water distance neutron noise detector delta t, delta time divided by delta time. Hence, the quantitative estimation or flow rate are calculated. Q equal V over A. So now it is okay. So now you have monotron. It's give you it's burst, and then you have first far detector and the near detector, and you can have a gamma ray further detection. So just excite or pump the oxygen and give gamma ray. This gamma ray will be picked by the receivers, okay, by detectors, and he calculates, and you know the distance, you know the time, and it will can give you a the velocity. The tool configuration. Based on the expected flow direction, the tool is configured either upflow if the cross flow comes from down to up or from up to down. Okay, so based on the expected flow direction, the tool is configured either upflow from here to here or downflow. So you can make the receiver in the top and the detectors in the bottom, or vice versa, if according to the expected the expected flow direction. The logging techniques involve taking stationary measurement while the well is flowing and shutting. The last one is cased hole resistivity. Cased hole resistivity is a technique. It's used. They use resistivity inside the casing. Okay, this is a primary evaluation on if you have an wells with no open hole logs, you can use this one. Location of bypassed oil. If you have bypassed oil, and if you have oil, you producing oil, and you expect that there is some oil in the reservoir, and you wanted to know if there is still oil or you produce it at all. So this is called the bypassed oil. Okay. In bypassed hydrocarbon, residual oil saturation, and reservoir monitoring. Okay. This tool, it is first of all, it's not continuous. It is a stationary measurement. It is not, you cannot take it on a continuous. You have to stop every 1 foot, every 2 foot, every whatever. You have to stop. Okay. So to measure. Second, it's very slow. Equivalent to logging speed 200 feet, 240 feet per hour. This is the most against this is a tool is the most disadvantage of this tool. The resistivity range is from 1 to 100. If any resistivity before 1 ohm, it will not see it. This is if so. If you have depletion and you have saline water and mechanical resistivity is very low, it cannot be seen. The vertical resolution 4 feet. A depth of investigation 7 to 32 feet. This is advantage because the RST it's only 8-inch, within 8-inch in the formation. The tool is just a lateral log. It just have an just enforce the current in the formation. Most of them go to casing, and some of them go to the cement and formation. The tool applied large current in casing downhole. Most of the current flow up the casing to the surface. A smaller amount flow down the casing, and a very small amount leak into the formation across the tool measurement section. To get formation resistivity, you must measure the amount of current that flow into the formation and the casing. So he have a total current, and some of them go to the casing, and some of them go to the formation. So he measures the this one in the formation and the cement, so he can calculate how much the oil, how much current, how much the resistivity in the casing. This is an example of difference between open hole and cased hole resistivity. The blue color is the casing here. The red one is the open hole. Thank you.
Thank you, Mr. Mustafa. If you have any question, you can open your microphone or leave it in the chat so Mr. Mustafa can answer it.
Any questions?
Okay, I think we don't have questions for today. So thank you all for attending today's second day for this workshop. It was a pleasure having you with us. And we especially appreciate Mr. Mustafa for sharing his expertise and hosting this wonderful workshop. So thank you, everybody. Have a good day. Goodbye.